It has been 2 years since NASA's James Webb telescope gave us a stunning first look at the depths of our universe. The $10 billion telescope is the largest and most powerful in space. It captured these images.
Yes, we expect James Webb to make great discoveries. We expect that.
In October 2017, the astronomical community was captivated by an unprecedented discovery. An object from another star system passing through our solar system at remarkable velocity. Named Oumuamua, Hawaiian for scout or messenger, this peculiar visitor has become the center of scientific fascination and speculation. The detection occurred when astronomers at the Helakala Observatory in Hawaii first spotted a faint point of light moving rapidly against the backdrop of fixed stars. Initial calculations revealed something extraordinary. This object wasn't following a closed orbit around our sun, but instead was traveling on a hyperbolic trajectory that would take it back into interstellar space. Unlike familiar solar system objects, this elongated, cigar-shaped body exhibited no comet-like tail and demonstrated unexplained acceleration as it departed our vicinity. These anomalous characteristics made it impossible to classify within conventional astronomical categories, sparking debates about its true nature. Teams of astronomers worldwide scrambled to gather data during its brief passage through our cosmic neighborhood, but conventional telescopes could only reveal so much. The object's relatively small size, estimated between 101,000 meters in length, combined with its rapid transit, made detailed observation extremely challenging. Now, the James Webb telescope has captured groundbreaking imagery of Oumuamua, fundamentally altering our understanding of this enigmatic traveler. The unprecedented resolution and sensitivity of this space-based observatory have finally allowed scientists to examine Oumuamua in detail that was previously impossible, revealing characteristics that have astonished even the most experienced astronomers and reigniting global interest in this cosmic wanderer. Defying conventional classification. Oumuamua's distinctive attributes set it apart from all previously documented celestial bodies. While comets typically release gas as they approach the sun, creating distinctive tails of dust and ionized particles, Oumuamua displayed no such behavior. Astronomers trained powerful telescopes on the object, expecting to observe the telltale signs of outgassing the release of frozen gases heated by solar radiation, yet found nothing of the sort. This absence was particularly puzzling given Oumuamua's close approach to the sun, where temperatures should have been sufficient to trigger substantial cometary activity if it contained typical volatile compounds. Similarly, it defied asteroid classification through its acceleration pattern, which couldn't be explained by gravitational forces alone. Careful tracking of its trajectory revealed a slight but measurable deviation from the path predicted by solar system gravity models. This non-gravitational acceleration, while subtle, indicated some additional force was acting upon the object. Traditional asteroids, composed primarily of rock and metal, don't exhibit this kind of behavior, leaving astronomers without a satisfactory explanation within conventional frameworks. This baffling combination of characteristics fueled diverse hypotheses, from naturally occurring hydrogen icebergs to extraterrestrial technology equipped with solar sail capabilities. Some researchers proposed that Oumuamua might be composed largely of solid hydrogen, which would sublimate without producing visible outgassing, potentially explaining its unusual acceleration. Others suggested exotic compositions of nitrogen or other elements rare in our solar system. The more controversial explanations ventured into the realm of artificial construction, perhaps a defunct probe or even an active technological artifact from a distant civilization. Without definitive evidence, Oumuamua remained an unsolved cosmic riddle until the James Webb Telescope's interventions provided new insights that would challenge all existing theories. The Webb Telescope's unprecedented revelation. As humanity's most sophisticated space observatory, the James Webb Telescope possesses unmatched infrared detection capabilities, allowing it to examine distant objects with extraordinary precision. Positioned at the L2 Lagrange point, far from Earth's atmospheric interference and thermal noise, Webb represents the pinnacle of observational astronomy. Its 6.5-meter primary mirror, composed of 18 hexagonal beryllium segments coated with gold, captures infrared light with unprecedented sensitivity, exactly what's needed to study a faint, distant object like Oumuamua. When directed toward Oumuamua, it produced the first authentic image of this interstellar visitor. The observation required precise calculations and tracking, as Oumuamua had already traveled billions of kilometers from Earth. Webb's instruments locked onto the object's predicted position and gathered photons over multiple observation sessions, combining the data to create an image that revealed details previously hidden from our view. This technical achievement, requiring coordination between international space agencies and research institutions, represents one of Webb's most challenging early targets. The imagery verified Oumuamua's elongated, asymmetrical form, while revealing previously undetectable surface features, indicating a long interstellar journey. High-resolution spectroscopy identified a weathered, reddish surface crisscrossed with subtle variations in texture and composition, evidence of micrometeorite impacts and cosmic ray exposure accumulated over potentially millions or billions of years. These features tell the story of an ancient object that has traveled through the void between stars, subjected to the harsh conditions of interstellar space for durations that dwarf human civilization. More astonishingly, the telescope detected organic compounds and elemental compositions entirely foreign to our solar system, suggesting origins in a dramatically different stellar environment. The spectroscopic analysis revealed complex carbon chains and molecular structures that differ significantly from those found in solar system asteroids or comets. Trace element signatures indicate formation under conditions unlike those that created objects in our own planetary system, potentially near a different class of star or during a different phase of stellar evolution than what our Sun experienced. These chemical fingerprints provide the strongest evidence yet of Oumuamua's truly alien origin, definitively confirming its interstellar nature. These findings offer glimpses into cosmic diversity and raise the possibility that Oumuamua might transport fundamental life-building components across galactic distances, potentially serving as a natural vector for panspermia, distributing biological precursors throughout the universe. The detection of organic molecules, while not evidence of life itself, demonstrates that complex carbon chemistry occurs in other star systems and can survive the harsh journey through interstellar space, preserving information about distant environments and potentially seeding chemical evolution wherever these wanderers eventually find themselves. Birth from cosmic catastrophe. Current theories propose that Oumuamua may have emerged from a catastrophic planetary disruption, possibly caused by interactions with a massive star or black hole. Computer simulations suggest that when planets venture too close to powerful gravitational sources, they don't simply fall in whole instead. They experience extreme tidal forces that can literally tear them apart. These forces differ in strength depending on distance, stretching objects along one axis while compressing them along others. The result can be elongated fragments with precisely the shape characteristics observed in Oumuamua. Such cataclysmic events could stretch and distort planetary fragments, potentially creating objects with Oumuamua's unusual characteristics. The violent separation process might also explain its unique rotational properties, as angular momentum would be redistributed during the fragmentation event. The Webb telescope's detailed imagery has revealed subtle variations in surface composition that align with this theory, different regions showing mineral signatures consistent with materials that would have formed at varying depths within a differentiated parent body. This layering effect provides compelling evidence that Oumuamua once formed part of a larger, geologically active world. If confirmed, this hypothesis transforms Oumuamua into more than a wandering object. It becomes a surviving fragment of a destroyed world, bearing physical evidence of its violent creation. The implications are profound. Each interstellar object like Oumuamua potentially represents a cosmic archaeological specimen, carrying information about planets that no longer exist. The distribution of elements across its surface tells the story of geological processes on its parent body, while isotopic ratios locked within its minerals could reveal the age and composition of its home system. The acceleration mystery. Perhaps Oumuamua's most perplexing attribute was its unexpected acceleration when leaving our Sun's influence. As it receded from the inner solar system, precise tracking revealed a subtle but unmistakable deviation from the expected trajectory. It was moving slightly faster than gravity alone would allow. This non-gravitational acceleration, while small, required an additional force acting on the object. Unlike comets propelled by outgassing, where escaping gas creates a rocket-like effect, Oumuamua showed no visible emission or coma that could account for this push. This discrepancy triggered intense debate within the scientific community. Some researchers suggested conventional explanations, perhaps extremely low-level outgassing below our detection threshold or subtle radiation pressure effects. Others proposed more exotic hypotheses involving novel physical properties or even artificial propulsion mechanisms. The controversy intensified when Harvard astronomer Avi Loeb suggested the acceleration profile matched what would be expected from a light sail, a thin reflective sheet that captures momentum from sunlight, technology humans themselves have developed for spacecraft like Japan's Ikaros mission and the Planetary Society's light sail. The Webb telescope's analysis detected reflective surface materials on Oumuamua that might explain this unusual acceleration. Spectroscopic measurements revealed regions with exceptionally high albedo reflectivity far greater than typical asteroids or comets. These highly reflective patches could potentially interact with solar radiation pressure in ways that would generate the observed acceleration. The telescope's infrared capabilities also identified temperature variations across the object's surface consistent with different absorption and reflection properties, potentially creating subtle thrust as Oumuamua rotated through the sun's light. However, whether these materials formed naturally or represent manufactured components remains an open question requiring additional investigation. The distribution of these reflective areas appears somewhat irregular, following patterns that could be interpreted as either natural variation or intentional design. Webb's instruments detected crystalline structures within these regions that have no direct analog in known solar system materials, adding another layer to the mystery. Scientists continue analyzing these observations, applying sophisticated models to determine whether natural processes in other star systems could generate such unusual materials, or whether more exotic explanations might be required. An ancient interstellar journey. Unlike objects native to our solar system, Oumuamua is genuinely interstellar, having traveled potentially billions of years across vast cosmic distances. Its hyperbolic trajectory, entering our system at approximately 26 kilometers per second relative to the local standard of rest, conclusively demonstrates an origin beyond our solar neighborhood. This velocity, too fast for capture by the sun's gravity, ensured Oumuamua would continue its journey onward after its brief solar system visit, eventually disappearing into the darkness between stars. Scientists believe it was likely expelled during the turbulent formative period of its original star system, when gravitational interactions between developing planets and their parent star could have launched it into interstellar space. During planetary system formation, complex gravitational dynamics between multiple bodies can eject substantial amounts of material. Recent observations of protoplanetary disks around young stars show this process in action as planets form and migrate. They scatter smaller bodies, some achieving escape velocity from their home systems. Oumuamua may represent one such ejected object, cast out during the chaotic early history of a distant planetary system. While its exact origin remains undetermined, the Webb telescope's data indicates a chemically complex birth environment, suggesting a star system with dynamics unlike anything previously observed in our astronomical neighborhood. Isotopic ratios of various elements differ significantly from solar system standards, pointing to formation around a different class of star with distinct nucleosynthetic history. The detection of unusual mineral phases implies crystallization under pressure and temperature conditions not represented in our own system, potentially indicating a more massive parent star with different elemental abundances or a more volatile rich planet forming disk. The significance of shape. Oumuamua's elongated, cigar-like profile presents another cosmic puzzle, differing dramatically from typical celestial objects. Initial observations suggested a highly elongated form, with dimensions approximating 800 meters long by 80 meters wide at 10. One ratio that far exceeds anything commonly observed among solar system asteroids or comets, where ratios rarely exceed 3:1. This extreme shape immediately raised questions about formation mechanisms that could produce such an unusual geometry. This distinctive geometry has prompted theories about extreme tidal stretching during close encounters with massive celestial bodies, or alternatively, formation as a fragment of a shattered larger body. Tidal disruption scenarios suggest Oumuamua may have once passed extremely close to a giant planet, neutron star, or even a black hole, where differential gravitational forces stretched it into its current form. Alternative explanations propose it might be a shard from a catastrophic collision between planets or a piece of a larger body disrupted by stellar activity, with its elongated shape representing a natural fracture pattern from the parent object. The Webb telescope's detailed surface mapping has revealed subtle striations running along Oumuamua's long axis, potentially supporting these formation theories. These linear features could represent structural stress lines from a violent stretching event or crystallization patterns from rapid cooling after a catastrophic disruption. The object's rotation adds another dimension to the shape mystery. Oumuamua tumbles in a complex, non-principal axis rotation, suggesting it experienced significant torque during its formation or subsequent journey. Its unique shape also influences its movement patterns, potentially explaining certain aspects of its mysterious behavior, including the unusual acceleration. The elongated profile presents varying cross-sectional areas to solar radiation as it rotates, potentially creating fluctuating radiation pressure effects that could contribute to its non-gravitational acceleration. This geometry also affects how the object interacts with the exceedingly thin gas of the interstellar medium and solar wind, creating subtle but measurable forces over long timescales. By analyzing this geometry, researchers hope to develop new insights into the formation and behavior of interstellar objects. The extreme dimensions challenge conventional models of astronomical object formation and stability, suggesting either unusual circumstances of creation or indicating that such shapes may be more common among interstellar objects than previously thought. If the latter proves true, it raises important questions about selection effects in our observations. Perhaps elongated objects are more easily ejected from their home systems or more readily detected during interstellar passage. Messenger of life. Beyond pure scientific curiosity, Oumuamua raises profound questions about cosmic interconnectedness. If objects regularly traverse between star systems, they might transport not just matter, but the fundamental chemical precursors for life. This concept, known as lithopanspermia, suggests that life could spread throughout galaxies by hitchhiking on natural interstellar travelers like Oumuamua. Microorganisms or complex organic molecules sheltered within such objects could potentially survive the harsh conditions of space for the millions of years required for interstellar transit. The Webb telescope's detection of complex carbon compounds and organic molecules on Oumuamua's surface lends credibility to this possibility. These compounds include structures similar to amino acids, nucleobases, and other building blocks associated with biological processes on Earth. While these molecules form through abiotic processes throughout the universe, their preservation during interstellar travel demonstrates the potential for chemical continuity between star systems. If such materials eventually land on suitable planets, they could potentially participate in probiotic chemistry, contributing to the emergence of life. While no direct evidence suggests Oumuamua carried biological material, its composition includes organic compounds formed in distant stellar environments. These molecules represent different synthetic pathways than those common in our solar system, suggesting diverse chemical evolution occurs throughout the galaxy. The detection of these compounds raises intriguing possibilities about universal biochemistry. If similar organic precursors exist throughout cosmic environments, life emerging elsewhere might share fundamental characteristics with terrestrial biology despite evolving independently. By studying such interstellar visitors, we're not merely examining isolated objects, but exploring potential mechanisms for life's distribution throughout the universe and the interconnections between seemingly isolated star systems. Each interstellar object becomes a potential messenger carrying information about distant worlds and the chemical evolution occurring there. Oumuamua's brief passage through our system has provided unprecedented insight into these processes, revealing that material exchange between star systems is not just possible, but probably common throughout galactic history. Technological innovation inspired. Oumuamua's brief appearance has transformed astronomical thinking, catalyzing new technologies and methodologies for studying interstellar objects. The realization that interstellar visitors may be relatively common has motivated development of new detection strategies and observation protocols specifically designed to identify and characterize these transient objects during their brief passages through our solar system. Observatories worldwide have implemented software upgrades to identify hyperbolic trajectories more efficiently, while neural network algorithms now scan astronomical data, searching for the telltale signatures of interstellar interlopers. From the Webb telescope's breakthroughs to conceptual rapid response spacecraft designed to intercept future visitors, scientific innovation accelerates. Engineers at multiple space agencies have drafted preliminary designs for spacecraft capable of reaching high velocities quickly, potentially allowing close encounters with newly discovered interstellar objects. These concepts include ion drives, solar sails, and even nuclear propulsion systems that could achieve the necessary speeds to rendezvous with fast-moving targets like Oumuamua. Advances in miniaturization allow consideration of swarm approaches, deploying multiple small probes to maximize the chances of successful interception. One particularly ambitious concept involves creating spacecraft capable of rapidly deploying to analyze future interstellar objects directly, addressing questions beyond Earth-based telescopes' capabilities. Such missions would require unprecedented coordination between detection networks and launch facilities, with spacecraft remaining in a state of readiness for immediate deployment. The scientific payload would include spectrometers, cameras, and potentially sample collection mechanisms designed to maximize information gathered during a brief flyby or rendezvous. These missions represent extreme technical challenges, but would provide invaluable direct observations impossible to obtain through remote sensing. As technology advances, our understanding of these cosmic travelers will expand, illuminating their origins and significance in the broader galactic narrative. Improvements in spectroscopic techniques now allow astronomers to detect chemical signatures at ever greater distances, while computational models have grown sophisticated enough to simulate the complex dynamics of interstellar object formation and ejection. New telescopes under construction will increase our detection capabilities, potentially allowing identification of interstellar objects much earlier in their approach, providing more observation time before they depart our neighborhood. Beyond Oumuamua, the search continues. While unprecedented, Oumuamua is unlikely to be unique. Astronomical models suggest thousands of interstellar objects may pass through our solar system annually, most too small or too distant for current detection methods. Statistical analyses based on Oumuamua's discovery suggest interstellar object detection rates that indicate a substantial population of these cosmic wanderers traversing our galactic neighborhood at any given time. If correct, we have only begun to sample this population of nomadic objects. In 2019, astronomers identified another interstellar visitor, Comet 2I/Borisov, which, unlike Oumuamua, displayed typical cometary features including a visible tail. Discovered by amateur astronomer Gennady Borisov using a homemade telescope, this object revealed itself immediately as cometary, with spectroscopic analysis confirming the presence of cyanide gas and other volatile compounds commonly found in solar system comets. Yet its hyperbolic trajectory conclusively demonstrated its interstellar origin, making it the second confirmed visitor from beyond our solar system. This stark contrast between the first two documented interstellar objects deepens the Oumuamua mystery. Why would one interstellar visitor appear so exotic while another seems remarkably familiar? This dichotomy suggests incredible diversity among interstellar objects, potentially reflecting different formation mechanisms, parent bodies, or evolutionary histories during their journeys between stars. The comparison between Oumuamua and Borisov provides valuable context, suggesting that interstellar space contains a rich variety of object types, rather than a homogeneous population. These discoveries prompt consideration of how many similar objects pass through our solar system undetected. Current detection capabilities are heavily biased towards certain orbits, sizes, and albedos, meaning we likely observe only a tiny fraction of interstellar visitors. Objects smaller than Oumuamua, those passing through the outer solar system, or those with extremely dark surfaces would easily escape notice even with current technology. This selection effect means our understanding of the interstellar object population remains highly incomplete.